This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Let me do that. You start talking. Is this all the text?
Yeah.
Okay. You start talking and I'll start doing.
Okay. Hi, everyone. Next Tuesday in Old Art from 12 to 2, there's going to be a semester 2 subject guide where you can find out more information from our students about core subjects, if you're deciding between biomedical engineering electives, or you're interested in doing the internship subject or doing the Japan research project over the summer. So that's pretty much it. Yeah. And there's free food if that's the only reason why.
Information here. Just in the nick of too late, the information's up there. So how are we going? All right? Hopefully you're coping and not as tired as I am. Me? I'm still smiling. How's that? Yeah? Thanks for asking. It's very kind of you. I think this thing's still ringing and I'll turn it off because I don't like it. Just on the bench. Okay, everybody who's coming in, notice this for next Tuesday? Yeah. Ethan's announcement. Good. All right. And I'll kill that and come back to where we were this morning, which was not that. But that. So this morning, I trawled through some old, some previous stuff on diode junctions, semiconductor junctions, and we discussed LEDs and photodiodes, and in fact solar cells as well. They fall into the category of optoelectronics, and we discussed how LEDs come in different colours, and you know that, and they're driven by different turn-on voltages, and we discussed this very simple example, and I hope you can figure out how all that works. If you don't, you better please come and see me pretty quick, because this is very simplistic stuff, and I would hope that you could deal with it in your current level. Mainly discussing the sensitivity of diode junctions, semiconductor junctions, to temperature in the first instance, and also illumination. So here's an example of a clinical thermometer, and I left you with these couple of extra slides to work through to make sure you understand how that works, how we can cancel out the very tricky and awkward bias that's very temperature dependent. If we have two such diodes with equal characteristics, both in terms of their geometric layout and also their impurity profile, their doping profile, so that they have roughly the same IS value. And if that's the case, then we can cancel out the two IS values to end up with a zero term following here, and the voltage difference between these 2 points can be indicative of temperature via this volt equivalent of temperature, which is kT on Q, so we can infer T from that. If we can organise the 2 currents. Now, there is an issue here that if we make the 2 currents equal, then we're in the same situation. We end up with zero output. So the currents in both diodes have to be different, known but different. Yeah? And you see what happens if they are the same current, then we get the log of 1 for this first term, and that's obviously going to be equal to 0, which is what we've effectively done with the second term, so it won't be of any use to us if we don't have 2 different currents. Good? Yep. If that's the case and we get the thing to operate, then we can measure with a differential amplifier, instrumentation amplifier if you will, between those 2 points, and we can decalibrate that for temperature. Because knowing the voltage between the 2 points, those 2 points, we know this voltage difference, we know the quotient of currents, so if we can remember kT on Q, then we can infer T. Good? Does that make sense? Hopefully it will in the future. Now I mentioned that there are also there's a family of other temperature sensors, some of which many of you encountered in biosystems design last year. Those of you who did that subject here will have come across this. You dealt with the thermistor, I think. Who played with the thermistor last year? Yeah? Okay. Anyone use a thermocouple? I know I advocated that for a few people, to try a thermocouple. No? And I did have some resistance temperature devices as well that I loaned to a couple of people. Who got those? I wondered where they went. And the one we're talking about here is the IC sensor. So this thing that I've just been talking about is the way typical IC sensors work. So who used them last year? Yeah? We got a bunch of those from Radio Parts, and a few people used them. What was it? The LM35? Yeah? Who remembers the LM35 from last year? Yeah? Okay, well that's basically what we're talking about here, and the characteristics are that it's very linear, its range is somewhat restricted, yep. So, it's got some thermal mass, so it takes time to warm up, and that thermal mass will incur what we call insertion loss, because in measuring, because it's got thermal mass, it'll take heat away from that which you are measuring, and that which you are measuring will cool down a bit as a consequence. Yeah? So that's something to bear in mind. There will be various counterclaims about the different sensors about how much thermal mass they are, and therefore how much using them will affect the measurement. Really depends on the housing. The very smallest one would be the thermocouple, because in essence it's simply 2 wires joined together. Yeah? I'll explain that, if not today then in another session. But it's got very, very little thermal mass. However, these things tend to be ruggedised for industrial applications, and they come in really hefty encasings so that they don't get broken, because after all it's just 2 wires joined together in this particular case, and you can see that up here. So they are vulnerable to being wrenched apart and otherwise broken. I dare say the other ones are too. Resistance temperature devices tend to be in fairly big encapsulations as well. They are basically resistive, so we run a current through them and measure the voltage across it. And you know, it's purely Ohm's law. These ones are extremely linear, and the downside is that they are usually made out of expensive materials. An alternate term for this is the PTD, platinum temperature device. And platinum tends to be expensive, and the various other metals, noble metals that are used for that are expensive. As the ones that other materials that are used instead of platinum also tend to be expensive, so they are vulnerable to theft. Misplacement, reappropriation. Anyway, they are expensive, so you have to be very careful. But they are kind of linear, very linear over a range, and their temperature range will far exceed that of the IC sensor. Because notice here we're stuck with 250 degrees where typical semiconductors stop working. But they can go to quite a high range. The thermistors, well, you guys used thermistors, didn't you, last year? Many of you used a thermistor. The problem with that is it's got a fairly hyperbolic relationship between resistance and temperature, so it needs linearisation. However, they are commonly quite cheap. That's why the university can afford them in abundance, typically. They're, you know, a couple of dollars sometimes for cheap ones. This is basically a resistor, and they can have low thermal mass, just sort of button thing, so usually not very expensive at all. What can I say? Oh yes, the resistive ones here are also susceptible to their own internal heating, so you run a current through them in order to measure a voltage across them. When you're running that current through, it's I squared R type heating. You know what I mean by I squared R heating? Power in a resistance is equal to current squared multiplied by resistance. If you don't know how that works, just think back to Ohm's law and use it twice, and you'll get the answer there. So that brings an error associated with it. And you have to use judicious choice of what you run through them. Now, the three on the right all require power supplied. The thermocouple is the one that you don't require power. Yeah. So it's got its own. It provides its own energy. As a consequence, as you might expect, it's got a very small output, very tiny output to be measured. Needs to be linearised because the characteristics are quite non-linear. Yep, I think that's about what I can say about that. The other method that's of interest to us in the clinical domain is the pyroelectric type sensor-based systems that are typified by the ear thermometer, and most people would have used one of those or seen them used in clinical settings or in the home even. Basically, it's a Boltzmann style black body detector, amplified up, and it needs to be normalised against or calibrated against an ambient sensor. So there's another sensor put in. It might be one of those other ones. typically in these scenarios, I should have mentioned that the thermocouple needs a calibration as well, and calibration usually falls back to the IC sensor, the one we've just described, because that is fairly programmable and reliable. Yeah. So that's one that we can use with confidence as being a value that we can rely on. Sometimes the ones like the LM35, you'll appreciate a $5 chip is not going to be as sophisticated as some of them can be, so the resolution is not fantastic. I think we got half a degree resolution last year, something like that. However, there are better ones, and some of those better ones are used for calibrating the reference point for thermocouples, and would be the sort of thing that would be used in your ear thermometer. The MUX here stands for multiplexor, and what that does is to, under control of the reading device, it can choose which of the, it's like a switch that is directs the input of choice to be the one from our sensor here, to be put through the analog to digital converter and compared via an algorithm with the ambient sensor to provide the digital display. There's also a shutter arrangement for timing the measurement, and that's all under control of the microprocessor. Yep. So that's the one that we see in clinical application with, once again, a different type of sensor, so I thought I'd better include that. You will have noticed perhaps in the clinical domain the skin temperature devices becoming more and more reliable and becoming more useful in clinical practice. Comments? The ear thermometer is still a little bit more of a silver standard perhaps, but you have to change the optical window, flick them into the bin and get another one, and that's a fixed cost for use. So the manufacturers like Braun and so on make good money out of their disposables. In this case, the little plastic windows that you have to change over every time somebody new uses it, or a new use of it. Yes? So if you're going to design a piece of medical equipment, factor in how you can make money on your disposables. What's a good example of that? The what?
The coffee machine where you have to have a packet of each coffee that you make at the machine. Coffee pods, coffee pods.
Yeah.
Because once you buy the machine, you have to use their specific brand coffee pod. Otherwise, you can't just that's a cafe one to that cafe.
Yeah. Good idea. I'll be back shortly. Thanks for mentioning that. I need it right now. So another example, yeah, that's a good one. Another example would be infusion pumps. When infusion pumps came on the scene, I'm told, it's a long time ago, so how would I remember? They were offered to hospitals at a bargain basement price to get them in. You know what I mean by an infusion pump? The automated pumps that clock various you know, they're used with lines, administration lines for drugs and so on in hospitals. You will have seen them on ER or whatever the TV show is at least. They have, in the old days we used to have gravimetric administration of drugs in bags, just be put in carefully measured with burettes and so on, I'm told. However, the automated system came in where this was under control and there was fixed boluses pumped in under control of a pump, and drips were measured and so on and so forth, sophisticated measurement techniques, optical arrangements to measure the lines, to count the drips. Now, when they first came in, pumps were being almost given away to hospitals at rock bottom prices, provided you signed up to use the consumable replaced giving sets. And they're always changed over, and the hospital administrators eventually realised that they should bargain more on those disposables rather than the pumps themselves. And hospitals are full of these pumps now. Yep. Okay, enough of that. Okay, the next issue that I'd like to talk about is isolation, and I want to talk about that a bit more here, but this is an application of LEDs and photodiodes. And the idea behind that is that in between the LED that's providing some signal in optical form, there's a barrier made by the distance between the transmitter, in this case an LED, and the receiver, which is a photodiode. Having said this morning that LEDs and photodiodes are really just two diodes that are optimised for slightly different behaviours. One's optimised to send and the other one's optimised to receive, to some extent reciprocal in their action. If you can organise it so there's a gap in between, that can mean an electrical isolation between, say, an item that's in a hostile environment over here, that the sending signal is in a hostile environment, say, and here we want to be safe, so we're over on this side. Or we might have something like a vulnerable patient over this side and a hostile environment over here. So the idea is here to isolate between typically something that's fragile and vulnerable over here and a hostile environment over here, or it might be to protect equipment, might be to protect an operator, or both. And one of the other things that we can do is to isolate from interfering signals as well, if we're careful with that. It's another alternative to common mode rejection, where we can actually keep a noisy signal out. So that's the concept, and you will have seen this before. Opto-isolators are used fairly extensively in digital systems for hookups of, computing and into the NBN, for example. It's quite commonplace everywhere these days. Okay, pulse oximetry. This is a method of establishing the degree of oxygenation in blood, and some of you guys will have used pulse ox sensor last year. Anybody? No? Okay, well, the way this actually works is by transmission of light through tissue, typically the finger or the earlobe, certain other sites. But if we transmit over two different wavelengths, typically the red down 760 or so, and infrared up at 900 or so, you might be able to pick up from here the difference between oxygenated blood, oxyhemoglobin, and deoxyhemoglobin. Can you see that down at this red range of wavelengths, there's a gap that's, at least I can say that's a positive value for deoxygenation, deoxyhemoglobin over oxyhemoglobin. So oxyhemoglobin is low, low absorption compared to deoxy at that level. And if we go up to the 900s, early 900s, it's the other way around. Small gap there. But that can be exploited if we're careful by making synchronous measurements for transmission under both those wavelengths. So we switch from one diode to the other, to the other, to the other, to the other, making measurements as we go. There's a little bit of smarts involved with it that I'm not sure I've got time enough to explain, but we can give that a shot. They can both use the same photodetector on the other side. If we select the one that will operate at both those wavelengths, and if we know which one's switching at any one time, then we can make a measurement and infer the difference between that and that to determine the level of oxygenation of blood. Yep. You familiar with that? Have you covered this in physiology earlier? No? I see eyes darting left, right, up, down. Does that mean yes or no? All right. In the new book by Webb, there's a little bit of discussion of this and how it's arbitrated. One thing I forgot to mention this morning, I should come back to that. I did mention to you that LEDs don't like to get too hot, correct? And they fail under heat stress. Another thing they don't like is being reverse biased. They don't like being operated as a normal diode to rectify. However, this clever arrangement here saves either one of those diodes, or either one of those LEDs from ever being reverse biased. Can you see how that would work? No? Let's see how quickly it takes me to get the overhead projector to work here. Let's hope it's being left in the right arrangement. Good. Oh, good. Okay. Right. We'll go with this one. How about I draw the characteristic of a typical diode? So we know that we have an off range here where there's a slight leakage current. And this is volts and this is current. And after we get to a certain point,
then things start to take off and head up skywards. And we have some sort of nominal switching point. Do you remember what it would be from this morning? Do you remember what it would be for a red LED? What would the voltage be here to turn on some current of around, let's say, 10 milliamps? Does anyone remember? Pardon? 2 volts? Not too bad. Anybody else? 1.7, yeah. That's typically the voltage that we allow for a red LED. Probably should be stabilised. No. You can do it. Say again?
Is it possible to turn off?
That's what I'm trying to do. How's that? No? Still going. Yeah, alright. I'll just try it out for the moment, and it'll come and go, and I'll come and go with it. In the reverse direction, a typical diode has a breakdown voltage in the negative domain after a specific point, and that depends on the way the diode's manufactured. So that will sort of sit. It just needs something to focus on, doesn't it? How's that? At a certain point, there will be a breakdown voltage here, and with LEDs, it's usually around 5 volts or so, something like that. So if we've got 2 diodes that are hooked up in the manner that I showed you before, that is, one's like this and one's like that, then what we have is superimposed. I'll do another diode characteristic up the other way, and maybe I'll do that with the grey LED. See if that fits. So, same sort of arrangement, but this time this is 1.7 here, and this is the 5 volts over that side. So the way that it works with characteristics like this, if you were to add, add 2 things in parallel, you would sum the currents that are provided by both. And in actual fact, what will happen is that this one will turn on in the forward direction, and this one will turn on in the reverse direction. So what I'm saying is that you never go into the breakdown region of either of those 2 diodes. It didn't work, did it? Because my theory. Okay. So they protect each other. And they're both switched independently. To provide their measurements separately. Now, Webb, who's got a bit of a treatment of this, talks about how that combined current is then put through a transimpedance amplifier, and I'll come to that in a minute or 2. That actually takes a tiny signal current that's out of the diode. That's the small signal part that sits on top of any bias component, and it's then filtered before it goes into the ADC for reasons that we'll discuss probably next lecture, next week. Okay, so we've got a signal train here where the LEDs are arbitrated in their switching by some smart arrangement that's hooked up to typically a microcontroller that decides when to switch these 2, and it knows when it switched them, so it can compare as it gets signals through from this analog to digital converter. So what we have here is all the way through here, there's a continuously variable in magnitude signal going into an analog to digital converter to digitise it in a form that can be then read in by a computer. Now this here is a bit of a filter, which is a bit hard for us to see. If you're going through Webb's book, which I'm starting to warm to, I must say, note that many of the diagrams are incorrect in terms of the usual fatal flaw of which is the inverting and which is the non-inverting input. It's unfortunate, but that's what's happened in this text first run. You don't make that mistake, though, do you? Because you know if you put these two around the wrong way, then what was previously an amplifier is now a comparator. Okay, and likewise, what might have been a filter will now be an oscillator. Possibly. Yep. So I guess you can appreciate that these two components here, what do they form? That resistor and capacitor. What kind of filter? Low pass filter, okay. Are you brave enough to suggest what the function of those two components, what filtering function those components together will form? Well, that's what a filter is a frequency variable attenuator, that's true, yeah. If we can accept that that's a filter, what will it be, a low pass or a high pass? Low pass, good one. And these two together. High pass, well done. Now, this is a little bit tricky. This is what's called a twin T filter, and we didn't cover that yet, although some people might have encountered it. Who's come across the twin T filter in your reading? We can make a guess at what it does, do you think? What would you say? This one and that one together do what? That resistor and this capacitor? Who thinks high pass? Who thinks low pass? Good. And these two together? Okay, so can you get the feeling that this might be a bandpass filter or a notch filter, depending on the relative values? Either it'll let a select frequency through, or it'll stop a selected frequency, one or the other. Yep. Okay, so that's a low pass filter, a high pass filter, another low pass filter. It's very similar to all those extra filtering things that you had in workshop 3, isn't it? Too much filtering, too much redundant filtering. I don't like this point here tapering off into nowhere. I don't like this point tapering off into nowhere. I don't like that tapering off into nowhere, but that's the way it is. The fact that it's in a big box here means it's kind of generic, so maybe we'll forgive it this time around. But I don't want to see that on an exam, please. Unless it's intentional, and I can't see why it would be. Do you understand what I'm saying? This returns nowhere, this returns nowhere, that returns nowhere. It's not good. Okay, so the next evolution, I guess, of this is to say what we can do is we can, after the analog to digital converter, we can use a digital filter here in the microcontroller to do some work on the signal that we can then restore to analog signal to provide an output signal. So one of the things about the oximetry signal is that there will be a background level to the signal. There's like a DC component, and there's the signal of interest riding on top of that. Maybe we'll see that in a minute or two. So what this is all about then is that there's some smarts for powering the level of the red and infrared signals respectively, because the sensitivity needs to be moderated for those two different wavelengths. Well, good. Now, here's a transimpedance amplifier. Can I ask you now to do some work? Just ignore the upper diode for the moment. Forget about this one. No, we won't. We'll forget about the lower one for now. And can you write an expression for V out in terms of I in? So this is a trans resistance amplifier. Trans meaning across, and resistance because the dimensions are V out over I in. You think you can do it? We won't worry about V in for the moment, but V in has some influence on things that I'll discuss shortly.
Do you assume that the amplifier is an ideal one?
Yes, assume the amplifier is an ideal one.
So ignore the diode part of that.
Yes, ignore the bottom diode. Okay, so assume that V in is 0 for now, is what I'm wanting you to do. Not yet. I haven't finished yet. You might copy off me. idea is that we've got an op amp that we presume is ideal, and we've got negative feedback. So that's a recipe for what at the input of the op amp. Good. Yeah, go ahead. Yeah, virtual short circuit. Yeah. Okay. Virtual short circuit, because it's virtual because the current doesn't disappear down a hole. It's got to come from somewhere, this IN. So the only place it can come from is through RF. Would you agree? Okay, so there'd be a voltage across RF of value IN times RF. And since this is notionally about 0 volts at that end, then V out is going to be equal to and so we can write a transfer function in terms of what would be a trans resistance. That would be V out on IN equals to RF. Good. Through the diode. That's the signal current through the diode. Now, there can also be some what we call bias current, some DC current that flows. Notice that these symbols here are lowercase symbols, so they're to do with the small signal part. If we were talking about the DC aspect, we might say that there's a DC value V out as a consequence of a DC current IN RF. Yeah? So that DC current can be provided if we make V in a DC value. So in actual fact we can reverse bias this diode, and it might be a photodiode. And if we reverse bias the diode, what happens to the depletion region in a reverse bias diode? Do you remember from this morning? Close. You're on the right. You're on the right track, but you're facing in the wrong direction, shall I say? It actually gets wider, doesn't it? Yeah. Depletion region will get bigger. What that means is that the collection area for incoming signal, photo signal, is going to be greater. So if we reverse bias, we can capture more photon signal. Does that make sense? More sensitive, perhaps. Alright. Okay, so going back to our previous circuit, what would you say would be the advantages of that circuit? Two advantages based on what we've discussed.
The protection for the fact that it's
Yep. Back to back. Yep. Good. And
something else to answer the next part.
it can operate in both directions, basically. Yeah. So that can be a detector for infrared and red, respectively. So we could use that for our pulse oximeter circuit. Good. All right. It's coming about the hour where I need a cup of coffee drastically. So can we have a 5 or 10 minute break? good. Who does a 3-minute coffee nearby here? The discussion of the Nescafe thing really got me interested.
Well, there's the coffees in the house. Steve and Steve.
Which is the quickest?
There's a cafe just right outside of the door. I don't know the name, but it's just right in the house.
The no coffee.
Yeah. Yeah, next to this is hot dog pizza in China Union. Yeah, it's just over there. It's on the corner.
got me. You got me. Okay, there's a couple of supplementary slides that I didn't have time to work into the discussion, so you don't have them yet. What I'll do is I'll wrap them up into a sample question so that you get exposure to it in passing. So basically, this was meant to show the differential between red and infrared. I'll just discuss it now and we'll give you the detail later. And also the so-called isobestic point is where the oxyhemoglobin and deoxyhemoglobin cross over. Now, I mentioned before that there's a background DC level which is due to absorption through the background unperfused part of the finger or toe or earlobe, and that needs to be subtracted out of the signal, if you will, and the way that is done is by normalisation of both the infrared and the red, which have different sensitivities, so it's a dynamic situation that needs to be managed basically. As I say, I'll give you a practice easy exam question that exercises these points. Okay, I didn't cover off it there, and we might not have enough time to really dig into it, but we can come back to it if we have time. Alright, so what I'd like to talk to you now about is to follow through on the information on the discussion on isolation, because there's a couple of other methods of isolation apart from optical isolation. Oh, you saw this stuff before, that's Ethan's thing that I stitched in there. Okay, so in general, the notion is with isolation that we have two areas that either of which might be vulnerable to the other, so we isolate one or the other. It might be electrical isolation, usually electrical isolation, and as I say, it might be to protect equipment, patients or operators. Two different areas. And we're developing up another symbol, as you can see. There's always a different triangular symbol for any of these things. The isolation amplifier is like a big triangle again, with a gap in the middle. So we've still got a triangle here, but now we've got a bit of a gap in between. That's an isolation barrier, and usually it's of hundreds of volts isolation, so that we can separate two supposed ground points. And one thing that's important is to make sure that these amplifiers are powered by separate grounds. I've seen some interesting things done where some folks have gone to the lengths of putting in an isolation system to protect one side or the other, and then they've powered them both from the same power supply, which kind of ruins the whole concept in the first place. So it has happened, I've seen it, not very smart. Yeah, after all that effort. Okay, so why do we isolate? As I said, it's protection of people and the equipment from hazardous voltages or leakages, and the byproduct is that we get another form of common mode rejection out of this. It's actually called isolation mode, but it gives us the same, or a very similar sort of result. And one of the other upsides is that we can eliminate those ground loops, and I'll come back to that in a moment. So once again, the symbology. I took this from Brown, which was an old company that did instrumentation work and made a lot of integrated circuits, and I've adapted it a little bit to put in Horowitz and Hill's new symbol for an instrumentation amplifier. The symbol for an isolation amplifier, as I've said, it has got that gap in the middle to indicate there's a barrier between input and output, and what isn't really shown is that this thing runs on two separate grounds as well. So, a very old application note from Brown. Became part of Texas Instruments, and many companies have done that. Okay, once again, here's the isolation barrier. Now, we can write the output in terms of input signal and common mode signal divided by common mode rejection ratio, and you'll be able to remember that common mode rejection ratio is differential gain divided by common mode gain. So the fact that the signal is not shown as being amplified by the differential gain, I guess you can figure that this is differential gain divided by common mode gain, so common mode signal is amplified by less than input signal. So there's another thing here, that's the isolation mode signal, which is what appears between the two earths. Can you see that the common mode signal is common to both of the signal inputs here? The signal input is common the signal input is differential. It's this input has the other input subtracted from it. The common mode signal is presented equally to both inputs of the both non-inverting and inverting inputs of the amplifier, similar to what we've seen before. Indices for the performance of the isolation amplifier are the isolation resistance and isolation capacitance, and the maximum isolation mode input signal between the two grounds. Another version of that here, showing that we can parameterize the error as a input referred error for both common mode signal and isolation mode signal. And once again, here's the gain amplifying, excuse me, this is differential gain here. So the common mode rejection ratio differential gain part will cancel out with this one here, and we're left with common mode signal divided by common mode gain for output. Oops. Okay, so how do we do it? As I've said, we've got two separate grounds here and an isolation barrier in between, and there'll be some passage of signal from across that isolation barrier. Here it's shown as being modulated on the transmission side, demodulated on the reception side. And what this is kind of indicating that there's a magnetic coupling, a transformer type coupling, which is one way of doing it. The other way, or in general, we have an isolation barrier with some form of coupling, modulation on the input side and demodulations on the output side. So the types. We can have the octocoupler that we've just been describing before. We can have a magnetic coupling or a capacitive coupling, and all three of those are fairly prevalent in the business. The thing about the optical isolation that we've just been talking about is that it is nonlinear. So subject to the Shockley diode equation, the exponential equation, this input signal, if it were not moderated in some way, would be reflected to output in a nonlinear fashion. So what's often done is to put a nonlinear element, another photodiode at the input of the sending end to, if you like, decorrupt or to corrupt the input signal to the same fashion as the optical sensor is at this point, the transmitter diode is over here. So the LED here will run to two photodiodes, one of which is at the input to kind of linearize output. Photodiodes, as I said before, we can put some bias on a diode to make it more reverse biased, and that will mean that we can get a greater light intensity, from a, sorry, back, from the sensor, because there's a broader collection area in the depletion region. So that bias condition is called the photoconductive mode, where some substantial bias is introduced, and along with that, because we have a broader collection region with bias, there's also some more noise induced in that sort of scenario. And it's faster because there's less capacitance associated with a reverse bias junction. For a zero bias junction, we don't have the noise, but we don't have the bandwidth as well, not as wide bandwidth. A unit that some students have used for projects before, that isn't as expensive as many of the others, is this one. That's a company called Infineon, I think, made this, and it needs some linearization. As you can see here, there's that extra diode presented at the input, and it gets illumination from the LED just as the receiving end does. There's this compensating diode in the input circuit as well to, if you like, pre-compensate, pre-linearise the signal. I think these were in the order of $15 or something like that, with 5 kilovolts of isolation, and I've known some students to actually use this to good effect. Haven't seen it for at least a decade, but it's a possibility for those of you who might be wanting to work in this space. Okay, another type of arrangement, as well as the optical coupled ones, are the magnetically coupled ones. Now, this is what's called a 3-port isolation amplifier. It's not only got input and output port, but the power supply for both ports is also separate. So there's isolation of power supply from both input and output. The power is actually pumped across the isolation barrier via this magnetic coupling. So there's signal coupling in a magnetic form across an isolation barrier, and there's also power for the input stage and power for the output stage, done as well, magnetically coupled across an isolation barrier. So you'll appreciate that there can be a degree of interference from each of these power supply arrangements to the signal path. So we would need to make sure that either the frequencies are different, the bandwidths are different for power at input and power at output from the signal pathway, or maybe we could map them all orthogonally to each other so the magnetic fields are not going to be coupled as well. Do you understand what I mean? So if a magnetic field is put up in one dimension, we might put the other one in an orthogonal direction and the last one in a mutually orthogonal direction, so we'll get less coupling in between the magnetic paths. There's someone nodding there, thank you for that. Some newer devices, I guess they're not really new now, but suffice it to say there's work going on in this space. The other technique is the capacitive coupling one, and that works pretty well also. Isolation barrier is an insulating gap, so the signal pathway is capacitively coupled, modulated from the sending end and demodulated at the receiving end. And I'm not really sure whether you can see it here. Can you see those twirly bits? That's actually the capacitive coupling arrangements that are organised so that they don't have a magnetic influence as well. So there's kind of very clever geometry there. Once again, these things are getting on a bit historic, but there are newer devices as well. And this one here is supposedly fairly cheap, more of a digital device than an analog one. Okay, this is the academic bit, I guess, and what it tells us is that whereas an instrumentation amplifier rejects noise by subtraction, cancellation, an isolation amplifier rejects noise by attenuation. So the isolation gap here has a galvanic resistance associated with it, and it is that which isolates out a common mode signal between input and output. So the mechanism, as you remember, with an instrumentation amplifier is that common mode signal gets neutralised by subtraction, the differential aspect. In an isolation amplifier, there can be an element of that subtraction still occurring, but the isolation mode signal, which sits across between the two notional return paths, the grounds. I use the term advisedly because the grounds are only reference points for each of those two sections. It's not as if they're forming a common ground. The idea is to make a separation there, and the isolation mode and common mode signals between are rejected by attenuation. Okay, so there we have it once again. Isolation mode noise between two different reference points or grounds. Common mode with respect to one ground. Cancellation occurring by subtraction. It kills off the common mode noise. The attenuation kills off the common mode as well as the isolation mode noise. Okay, do we know enough about bridge circuits to understand how this one works, I wonder? Let's see. Okay. This has got two things going on with it. It's got an isolation mode amplifier, and it's got a bridge circuit here that's got ostensibly a sensitive element to it. It might be sensitive to temperature or strain or some other parameter. The resistance might change with respect to that parameter, thereby changing the bridge voltage. The potential divider here might change in response to an increase in resistance pushing this voltage up, or a decrease in resistance bringing this voltage down. Either way, we expect this point here to be remaining the same. Now, can you tell me why, if this point is at 2.5 volts, why necessarily this point here will be at minus 2.5 volts? How would that happen? This device here is meant to provide a reference voltage from some supply that might vary a bit. So it's meant to have a regulated output of 2.5 volts. Why would this be minus 2.5 volts?
Is it because of the virtual ground?
Perfect. Well done. It all comes back to that virtual ground business, doesn't it? So how do we get a virtual ground there? Remind me.
At the OPA 130 op-amp,
Yep.
there's a virtual ground between the inverter and non-inverter.
Correct. Yep.
And that tracks back to that point in which we
Yep.
release the bridge.
Okay, so this is going to be 0 volts here as a consequence. Yep. All right. So if this point is 0 volts and this is 2.5 volts, this is a symmetrical bridge. So there'll be a current flowing through this upper 1K resistor. Where does it go? Well, it doesn't go there because this doesn't draw current. It doesn't go there because this doesn't draw current. It's got to go through this resistor down here. And it'll be the same current flowing down that way. What will the value be? Good. Okay. So we've got 2.5 milliamps flowing down here. Doesn't go that way, doesn't go that way, it's got to go that way. So it will set up a voltage across this resistor of value 2.5 volts, okay. And 0 at this end, so this end's got to be minus 2.5 volts. Agreed? Good. So plus 2.5 this end, minus 2.5 at that end. So we've got 5 volts across a voltage divider here, where this voltage will vary depending on what happens to this one variable resistor. Okay? Does that make sense? Who has difficulty following that? Please be honest. All right, so a variation in resistance here. Question? Okay. This one here. All right. Do I need to go to the dreaded
Big stick.
the big stick? Yeah. Sure. We'll see if we can do it discussion-wise. Are you good with us having 2.5 milliamps flowing down that way? And are you good with 2.5 milliamps being confined to flow down there? Yeah? So we've got 2.5 milliamps flowing across this resistor, and it's a 1k ohm resistor. What voltage is set up? What voltage will 2.5 milliamps through a 1k resistor provide? 2.5 volts, okay. And this is the zero line, and we got 2.5 volts coming down from the zero line, correct? This 2.5 volts is plus 2.5 this end compared to minus 2.5 that end. But this end is fixed at 0 volts, so this is below ground level, if you like. Does that make sense? Yeah. Right, good. So the op-amp output is just doing what it needs to make these two inputs track each other once again. Okay. It's tricky, isn't it? Okay, so if this is minus 2.5 volts because this is plus 2.5 volts, we've got 5 volts across that bridge. We've got 5 volts across this potential divider on that right-hand side of the bridge. Yes? 0 volts in the middle, but don't forget this resistor can change things, so that point can be somewhere between minus 2.5 volts and plus 2.5 volts, depending on how extreme the value ends up being here for that resistance. So in response to some stimulus, this resistance can change, pushing this voltage up or pulling it down. Good. We don't have to worry about that. Yeah, this was an example question. I've got 2 example questions here. I think they're in the, they might be, I think you've got these on the slides. Okay, here's a similar sort of thing with an isolation amplifier here with a gain of 1. So VO is equal to V2, fairly simple. And an op-amp in the vulnerable side. So this is a big motor here that is susceptible to extreme voltages, perhaps, something like that. So to sense the current in this motor, there's a series resistor measuring across here, and we need to figure out what the resistor values need to be to provide an output of minus 10 volts. So that's with a 50 millivolt drop across the resistor. So typical sort of question. This might have been some sort of patient circuit, you know, defibrillator or something like that with a very high voltage. In this case, it's an industrial motor scenario. So that's the sample question for you to work on. And some references there. This is, I should have put bibliography here. It's not references for you to go and read up. It's just my being polite to the authors who provided me with resource material. So please don't think you have to go to all this, but you can if you want to. Okay, any questions at all on all that stuff? What are the main points here? How many methods of isolation are there? How many methods of isolation did we cover? 3, okay. If I can say that some are 2-port and some are 3-port, did I make a mention of that? Maybe I didn't.
When you isolate, if you isolate power,
Yeah, okay, so which ones of those 3 are 3-port and which ones are 2-port?
would capacitors and for the photodiodes and LEDs be 2-port and the magnetic be 3-port?
Great, thank you. Well done.
Was a guess.
Not a bad guess, yep. Okay, so how does an isolation mode amplifier reject common mode signals? Sorry? Attenuation, yeah. As opposed to an instrumentation amplifier, which does it by cancellation. Okay. Good. Any other issues? I'll just put that up for you, and I guess we can finish up there a little bit earlier for a change. All right. I mentioned this morning that I have initiated a bulletin board forum, but you can't see it yet because there's some tricky switch that they haven't told me I have to do to make it visible to students. Even though I've made it visible to students, it's not visible to students. I'm fairly hapless with these things. I do apologise. I'll take advice tomorrow and hopefully we'll have it up and running by Monday. Yeah. Once again, tomorrow's workshop. Once again, tomorrow's workshop. Continue on with workshop 3. Those of you who have finished, who's finished, can move on to workshop 4, and I'll try and post that overnight. Who's still working on workshop 3? Can use more time. Anybody here who hasn't gone through the test paper with me, mid-semester test? I think about 4 people whom I haven't discussed with. So if you're going to be at the workshops tomorrow, we'll make a time and have a chat. Yeah, I think there's only a handful, very few people who fall into that category, but it'd be good to have a chat if we can. And otherwise, we'll see you tomorrow at the workshops. Good. I've still got your Yeah. Just a moment. Just check this. Sorry about that.
Like for this ECG amplifier, did that specifically mean those this part, or just the whole part, the whole stage?
This whole thing. That's the ECG amplifier.
Yeah.
That's in the box. That box there is this box here.
Okay.
Whole thing.
The whole thing is the power, and also the what should be the theoretical limits
Of
of the ECG?
that's something you have to work out.
Yes, it's just wondering if that means we write down the
Transfer function.
Yeah, transfer function for this the whole stage, and work out or after the modification.
Which modification?
Because
You changed it.
Yeah.
Okay. Well, you have to tell me about that. You can tell me what it was before
yeah.
and what you changed it to theoretically and what happens afterwards.
Okay. So you calculating the according to the circuit, and then you simulate and record that result and compare. Oh, okay. And yeah, this one is the same order. How do you get the same order with four amplifiers?
Well, it matters what the value here is. That will change the common mode rejection ratio. You can give component names like R1, R2, R3, R4.
Yeah.
You can write common mode rejection in terms of those resistances if you like. And there will be common mode rejection in terms of the op-amps, internal common mode rejection, if you want to go that far. And you did that in biosystems design last year. I know because I was there. So you took into account the common mode rejection of the op-amps as well. Yep. Good.
Yeah. Yeah, I think that's it. Yeah.
Sorry.
Yeah, I think that's it.
Okay, good.
Thank you.
Pleasure.
See you.
See you tomorrow. Long hair's fine. Oh, yes, that's right, probably better. Oh. Hello. All right, how are you? Thanks for waiting till 5 o'clock. Pretty kind of you to do that. Yeah. No, it's perfect. Yeah, just my lecture actually finishes at 5:15, but I cut it short. Just, yeah, I really must have known you were coming. I won't kiss anything. Sorry? He hasn't been fantastic last night. When I went to see him, he was asleep, but Nancy rang me because she was in tears